All right, for those of you who are online now, just going to wait a few more minutes here for everyone to come in and to make sure everything is working. All right, we still have a few people filtering in. Does everyone have notes who wants them? For those of you who are online, the notes are also available in Blackboard if you go to the master course. All right, well, today there was a little bit of short-term pain, I hope, for long-term gain. I've been in this room for about the last 3 hours trying to get this working, and it's mostly working. And I believe everyone is able to see the screen exactly as you're seeing it through YouTube. And what's that? Oh, yeah. And this I've learned since last week how to do. All right. So yes, and I do have my email window open right next to here, so if anyone who is remote emails me a question, I should see it right away and answer it. Maybe don't put it under a previous email, but give it a new heading with a question and I'll check it. So we have about a dozen people, it looks like, who braved it in here from the storm, and I thank you all very much. I would have felt really funny sitting here talking to an empty room. Hopefully it'll make it worth your while. So today is going to be a continuation of talking about the data types, variables, and some ways of looking at them both graphically and numerically. It's kind of a continuation of last class. Let's see. Okay, here we are. So yeah, we're going to review the stuff again that we covered in the last session, which is going to include frequency tables, which you talked about, and we'll talk about a few important kinds of plots of data. This is funny, I can't see the whole. There we go. Some of the oldest, most important statistical methods, the mean, median, and mode, which, as I mentioned last class, I think are important, and still I use them every day. Maybe not all of them. I certainly use mean, I'd say, every day, and also cover some ways of measuring spread. Let's see. Okay, so we learned a few new pieces of vocabulary last class, and the important ones of these were population, which is a well-defined group of interest that we're studying. So population, depending on what we're doing, might be everyone in the world, it might be everyone at Hunter College, it might be everyone in the US, but it's some population that we're interested in, and that normally we can't observe the entire population. So instead we use samples, and much of statistics is about taking samples to learn something about the entire population. And anytime you take a sample, there's going to be some uncertainty because you don't know everything, you just know about part of it. Records observations, every time we go to one individual in that sample or in that population and record some things about them, that will be a record. So records have to do with individuals, and variables, which I'm going to be talking about, are the different things that we measure about one of those individuals. And then descriptive statistics, which we talked about, is a lot of what we do, and it just has to do with describing the data, not necessarily testing a hypothesis or making an inference about something, just describing the data that you have by looking at it, by making some numerical summaries, and that's what we're going to be covering today. Then inferential statistics we'll spend lots of time in on this course after this class, and that's where you actually make decisions based on your data. So a variable, that is any characteristic recorded about one of the individuals in our sample, and there are a few kinds of variables that we covered. Nominal, those are the ones that are just sort of nominally a number. They're not numbers in the traditional sense, and that we can't do arithmetic or anything. The only thing they do is encode when two observations are different. So examples were gender, race, marital status, anything that just has distinct values. And ordinal variables are sort of a special case of nominal variables, in that there is an order to those distinct categories. And I should mention here that sometimes nominal and ordinal all get lumped together and called categorical variables. So this isn't a totally agreed on notation, and you will sometimes just hear categorical variables referring to anything where, you know, there are categories. It's not a true number. And then quantitative variables, these include both discrete and continuous variables, and these are just variables where they really are numbers. So they're weight, height, things that you can do arithmetic on. You can add, subtract, and those would be continuous variables. And then a discrete variable would be something like number of children in a household, things that only take discrete values. And sometimes the line between discrete and continuous can be a little bit blurry, and it just depends on how many different values that you have. If something like number of children in the household that varies maybe between 1 and 5 in your study, that's very clearly discrete, and something like weight is very clearly continuous. Okay, and we covered a couple ways of summarizing these as frequency tables, which is just a list of how often each of your discrete or your categorical nominal variable occurs. And these can also be summarized visually as bar plots. And note, I didn't talk about pie charts last time, and that's because most statisticians don't like pie charts that much, but maybe that's just because they haven't seen a pie chart like this. This is an excellent application of a pie chart. The pie I have eaten and the pie I have not yet eaten. You can tell exactly what it means. The reason some statisticians don't like these is that it's not that easy to actually look at quantitatively. Like if you look at that, can you tell what proportion of the pie I have eaten? You can kind of tell, but you know, not too accurately. You can tell accurately enough for the purposes of knowing that you shouldn't eat the rest of it today, but generally, anything that you can do with a pie chart, you can probably do better with a bar chart. And there is an example of what a bar chart for this would look like. And it's definitely not as interesting, but you can tell a little more accurately there exactly how much has been eaten. You can see it's about 0.35 that has been eaten, or 35%. So that's why we usually like bar charts better. And these frequency tables, as I said, those are just an adding up, a counting of the values that occur. As an example, we have 4 out of 40 students receiving an A in a class. Then the frequency of of A's is just 4. The proportion is, you divide that by the total number, so 4 out of 40, that's 0.1, and the percentage, you multiply that by 100 and get 100. So those are all of the different ways that we can numerically describe a nominal or categorical ordinal variable. And you can use any of those in a frequency table or a bar plot. So I showed examples of putting the frequencies in there in a frequency table, but you could just as well instead put decimals or percentages in there. It's same thing. So moving on then to quantitative variables. I'm going to go over 3 different kinds of visual summaries, and then we're going to go over some numerical summaries also. The 3 kinds, and there are lots of visual summaries, graphical summaries. I'll just talk about 3 of them: the dot plot, the histogram, and the box plot. And generally, these are going from top to bottom, from the most detail to the most summarization. So with the dot plot, you have as much detail as possible, but sometimes that can be a bit confusing. And in the box plot, you have the least amount of detail in terms of individual observations. So I'll give you some examples of those, but you can use these. You know, when you see some data for the first time, it's probably a bunch of numbers, and these will help you go from like pages and pages of numbers to something visual where you can start identifying things like where the center of the data is, the spread, skew, and outliers, and I'll explain all of those to you in a little bit. So a dot plot, it's just showing every single observation. I showed an example last time where there were little dashes. Here's an example where there are dots, and in this example they've also been stacked up a little bit. So it's kind of like a histogram here. But the point is that you actually see every single data point. So this is only very good for small data sets. When you have more observations, a histogram is probably a better bet. And this is doing some summarization of the data by taking it and putting it into discrete bins. So in this example here, I don't know if I do have. So instead of showing every individual value, it's been split into bins here of this is like 100 to about 100 and 17 or something, I guess, and you're just counting the frequency of how many times that happens. So you can see there are 3 observations that fall within the range of that first bin. And you could also show, instead of frequency, show proportions there. That's a common thing to do if you want to see proportions or percentages instead of counts. Yes, question?
When you say bin, what exactly are you referring to?
Okay, the question for those online is, when I say bin, what am I referring to? I'm referring to each one of these rectangles as a bin. And so so you could think of it as you actually literally like a bin, where the bin has the width that you see here, and then every time you see one of your quantitative variables that's within the range of that bin, the width, you just stack it on top. What's that?
So like clusters.
What do you mean by clusters?
You put in stuff together.
Yeah, you're putting stuff together. That's right. So you imagine that this is like one of those. Well, imagine it's a bin, and that every data point has a width of like 1 inch or something. Every time you add an observation into that bin, the height of the bar grows by 1 inch, and it's a bin just because it's something with a certain width that collects any observation that falls within the boundaries of that bin. Any questions? I haven't seen any questions from online yet, so I'll just assume there aren't any questions online. So when you make a histogram, you have to choose a bin size, and your software will probably have a default that it chooses for you, but you should know that it is an option, and it's just making a guess as to what might look good. But you can change the width of these bins, as this example shows. On the left there, they're very, very narrow bins, so you are not going to get very many observations going into each of those bins, and then they're getting wider and wider, and on the right they're quite wide, so we have a lot of observations in each bin. So there's more summarization happening on the right and more detail on the left. And in the extreme case of going to very narrow bins, you could actually get to the case of basically a dot plot, where you have no more than one observation in any one of the bins. So this is kind of this trade-off between more detail and more summarization is something that you'll face when you do descriptive statistics, and you just have to decide. There's no right answer either about which plot to look at, how to break up the bins if it's a histogram, but they're just choices that you should be aware of and be ready to look at some different ways and decide what communicates your point the best. So when you look at a histogram, the main things that we're looking at are the center, the spread, and the shape. So the center is just kind of where where is it the highest in the histogram, where does most of the data lie. The spread is like how wide it is, and the shape, is the shape of it. And I'll give you some examples of what I'm talking about there. But the biggest things that we're looking for are symmetry and outliers. So here's some examples of shape and skew, and this is showing these as a continuous curve, but histogram, it's the same thing. This is what I am talking about by a symmetric distribution. So this is a quantitative variable with a symmetric distribution, and so if you take the most common value, you have equal amounts on either side. So this is something I think generally if you looked at, I don't know, weights of something or a lot of things will have this kind of distribution, and we'll be talking about this distribution a lot in this course. But it doesn't always happen that way. There are distributions that are skewed to the left. This is what we call left skew, and this is what we call right skew. And I don't know, an example of a right skewed distribution that I know of is rental or real estate prices in New York. And that is when you have a lot of places that are kind of on the low end of the cost, and then you have fewer and fewer at very high prices, and that upper tail goes on for a long ways to some very, very expensive places. I think there are probably lots of examples. I just saw a question from online, so I'm going to take that. Does more summarization versus less result in a loss of data for histograms? Thanks, Peter. And the answer I give to that is yes. You are losing information as you do more summarization. I wouldn't exactly call it loss of data, because data are the numbers underlying the histogram, and that's not changing. But the information, the amount of that information presented in the histogram is reduced. So in the extreme case, I'm just going to go back to let's see. It's not letting me back up. Apologies. Okay. So yeah, as an example here on the left one where we have the smallest bins and we're showing the most information, you can see that there's one somewhat extreme value here. This is not much of an outlier, but it's a bit. But by the time you get to wider histograms, you can't see that as well. And you know, there are other cases where maybe you would have some area in the middle where there's a gap, and with no data points, you're not going to see that anymore when you get to wider histograms. So it's funny, I would expect to be having the trouble with the Hangout, not with PowerPoint, but okay. So some examples of skewness. Lifespan is a left skewed distribution in that we have quite a few people who live to be in their 70s and their 80s here, and a few people who die at younger ages. So we end up with a left skew, and we don't have a whole lot of people who live really a lot longer than I don't know, 80 or 90 years. So you know, maybe the maximum, the highest outlier would be like 110, which is only, you know, 20 years or so older than somewhere around this middle, but on the lower end it goes for much further. So it's a good example of a left skewed distribution. And incomes like housing or rental prices that I mentioned, very right skewed. Is this all making reasonable sense so far? Any more questions? Okay. Okay, so skewness is one kind of shape that we'll look for. Another one is modality. So sort of the, I don't know, this says the type of the mound, but on the left, this looks sort of like a pile, the histogram. That's a unimodal distribution. The mode being the most common value is, and I'll talk a little bit more about in a couple pages, and it's called unimodal because there's just one most common value here. And on the right is a bimodal distribution because there's still only one overall most common value, but you can see there are kind of two separate distributions here, and each one has their own mode. They don't always look quite as well separated and distinct as this, but it is something that can happen. An example I could think of would be potentially, well, say you go to a room where there are parent-teacher interviews of a grade 4 class, and there's some parents and teachers, and there are children there, and you measure the heights. That's going to be a bimodal distribution, where the children have sort of one distribution of heights that's probably going to look kind of bell-shaped like this, and the adults have another distribution. So often when you see that, it's possible that there's some structure in your sample or in your population that is getting lumped in together. And finally, outliers. And outliers are what they sound like. They're a data point that is just way out from the rest of the distribution. It doesn't look like it belongs there. We want to be aware of these outliers. They can be there for different reasons. Sometimes you might find an outlier because it's the way someone coded the data. Maybe they were using 999 to mean missing or something, and so you see that it's an outlier. You need to investigate it. So in general, when you see an outlier, you want to try and figure out why it's an outlier. You don't necessarily just want to get rid of it, because that may very well be part of your population, and if you ignore it, you're actually biasing your analysis and ignoring data that might be telling you something that you weren't expecting. So be aware of outliers, try to investigate them, don't just throw them away though. So finally, the box plot, and I think I showed you this figure in the last class too. It's a complicated one though. I do want you to start getting comfortable with box plots, because they're an underused but really, really useful visualization tool. And once you start getting used to how to read them, then they're not so bad to use, and they are used in publication, in academic publication anyways, quite a lot. I use them all the time. So this is even more summarized than the histogram. What we plot here, this box, the box shows where the middle half of the data lie. So that's between the first quartile and the third quartile. And I'm going to talk more about exactly what I mean by quartiles, but you're probably somewhat familiar with the idea of percentiles, like when you take an exam, a standardized exam. If you score in, above the 50th percentile, you've done better than half of the people, and that's what this middle line shows you. That's the 50th percentile, or the median. The other two boxes are the first and third quartiles, the 25th and the 75th percentiles. Then these so-called whiskers extend out. Well, you don't really need to know where they extend to. They extend out to the from the box another 1.5 times the so-called interquartile range, which is the width of the box. So this is 1.5 times the width of this box, or the furthest point out. So it can be shorter than this, but it never gets longer than 1.5 times the width of the box. Don't worry about it. It's the point of the whiskers is that if you see data points outside of them, you can think of those as outliers. So this is just it's a very compact representation. This is much more compact than showing an entire histogram, and it lets you put things side by side, which I'll have some examples of. If you have questions about this, I recognize this is a complex plot, and I've been in research meetings where I'm presenting something to a group of clinicians, and everyone is confused. The first time you see a box plot, it doesn't make any sense, but it starts to sink in after a while. Any questions about the box plot? Okay. So the big reason why we use box plots instead of histograms sometimes is so that we can compare two distributions. So this example, height of males and females, we can just compare these side by side, and this would be much harder to do with histograms. And this could be extended to a categorical variable with more than just two values. There could be 5 or 10, and we could just put more and more of these boxes side by side. And they can be showed sideways like this or vertically. It doesn't matter. But by putting them side by side like this, you can just immediately see, here are the medians. So the median, also the interquartile range, that's the area of the box. All of this is higher for males than females in this sample. So it's a very easy, direct comparison of two quantitative distributions. Okay, I'm going to move on to some numerical summaries of these quantitative variables, and I'll still be making use of these same plots to show you some of that, but I guess this is the first really new stuff from today that we didn't cover at all last class. So mean is the average. It's probably what you have, I'm sure you've roughly calculated it in your head before. All you do to calculate it, if you have a group of numbers, is you add them up and you divide by the number of numbers, or the number of observations. I'm showing it to you here in so-called capital sigma notation. I'm not going to, if you don't like formulas and it scares you, that's okay. It's not a formula-based course, but you should be aware of what this notation means. Anytime that you see this is the Greek capital letter sigma. It just means sum. So the way you would read this formula here, x sub I would be your data values, where I is your individual. So this is an index. I could be number 1 for individual number 1, number 2 for individual number 2, and n is the total number of individuals. So if I were going to calculate an average of something for everyone in this class right now, I would give each of you an index, 1, 2, 3, 4, 5, and now we're maybe up to about 15 or something like that. So this would just say, if we were taking an average height, xi would just be each of your individual heights, and this would say add all of those up until we have n, which is the total number of people in the class, and then divide by that number. So that's not too bad, right? It's a formula, but do you think now you could look at this formula and recognize that that means average, and know that to calculate an average, how you would do it? I see a little bit of, I see some nodding, I see some kind of suspicious looks in the audience. I can't see people outside at home at all, so is it fair to say that average is a pretty familiar, comfortable concept? Yeah. Okay. I'm gonna go on. I am gonna show, I think, just one more formula in this class, but don't let them scare you, please. So the mean, important thing to know about it is that it is not resistant, and I'm going to classify each of these summaries that I tell you about today as resistant or not resistant. And by not resistant, I mean that it is influenced by outlying values. So one real outlying value can change the mean quite a bit. As an example, if a group of people go out to lunch and everyone just orders an appetizer except for one person who orders everything on the menu, you'll have several $5 and one $100. The average is going to be brought way up by that $100. And if you don't want to be paying for that person's lunch, then maybe you wouldn't want to be paying the average amount into the meal. This is just some examples, just to start getting you familiar with box plots and thinking about the influence of outlying values on the average. I simulated 4 different distributions. You don't really need to know what these are. The only ones that we'll actually cover in this class are the normal distribution and a uniform distribution. Just in case you're interested, this is just the log of a normal distribution, and this is an exponential distribution, which is the exponent of like 10 to the values in a uniform distribution, but it doesn't matter. The only thing that matters here is that this particular distribution, this log normal distribution, has some really extreme outlying values, and this one in the middle here has some skew to it. So I've plotted, so this is a kind of a fancy box plot where I added the individual data points to it. And in red, I put where the mean is. And of course, the middle line in a box plot, that's the median. So for the normal distribution, which is nice and symmetric, you see that this red line, the mean, is right on top of the median. And that's the same thing for the uniform distribution. It's just a little bit off, and that's just because this is a random sample. And we'll talk lots and lots about random samples. But the point is that things can be a little bit, they're not going to be perfect in a random sample. But it's pretty close. The mean is equal to the median when we have a symmetric distribution. In these 2 middle cases here, what are skewed and have outliers, you can see this mean being drawn above the median, and that's the influence of the outliers. Does that make sense to everyone? Any questions? Yep.
Is there going to be a point where we'll have to use those for the mean in the exam? Is there going to be using those symbols? In the other mean, you want to
Oh, the sigma notation?
Yeah.
No, I'm not going to get you writing formulas down in the exam. Yeah. No, I just want, I want to expose you to some things, and you'll see that notation in the textbook as well, and you might see it around. So you'll know what it means. Okay, so the median, which I've been talking about a bit already, just to formalize what it is the midpoint of your quantitative observations if you order them. If you have an odd number, it's just that middle observation. If you have an even number, then it's halfway between your two middle ones. And it's also the 50th percentile. And I've got a couple examples here of calculating the median. So here are the 1, 2, 3, 4, 5. Anyone know what the median is? 3. Yeah, I guess I bold-faced it so you can see. In the second one, 1, 2, 3, 4, and 100 million, what's the median? 3. So that's what I mean. It's resistant to outliers. You add an outlier to it, and it doesn't change that median at all. It's very resistant to outliers. And just to show the even number example, if you have 1, 2, 3, 4, your median is 2.5. That usually doesn't matter too much. You would only notice that when you have a very small number of observations like this. If you have some dozens, probably there isn't going to be too much difference between your middle couple values and the median. But it's halfway between those two middle values. So one more example here, and just to make it a little more visual, if you want to know the median height of the 7 dwarves, you would just line them all up from shortest to tallest. You'd probably get them all to stand, unlike here, but then the median would just be that height of the 4th dwarf when they're all lined up like that. So it's an actual height of one of the individuals. And if you were to add instead Shaquille O'Neal, the median, of course, is still the same. It's still the height of the middle dwarf. I know Shaquille O'Neal was only with the Celtics for a little while, but I was in Boston while he was there and saw this appear in the Boston Globe and thought this was they were showing the height of, it was the big snowfall year, and they're using it as an infographic to show how much snowfall there had been as it buried Shaquille O'Neal, which I really liked. I'm not even a basketball fan, but. Okay, so the mode is just the most common value. So if it's a histogram, or a bar chart, it's just the tallest bar. So in this case, of course, if it's quantitative data, the mode isn't exactly well defined. You need to have some binning like this in order to say what the most common value, because if every value is unique, then there is no mode. But once we start grouping them together, then we can actually count where most of the data lies. So can everyone see in here which bar is the mode? Yeah, it's this second one there. That's the mode. So of course that's not an exact value for this data set. That's a range from, it's a range from here to here. So from about 130 some to 150, that whole range, that's the mode. And of course, if we change the histogram by changing the bins, the mode might change. All right. Okay, and as you saw in that box plot before, skewness will pull the mean away from the median and also from the mode. So even if you don't plot your data, if you look at the mean and the median, you can infer whether there's skewness just by a difference between the median and the mean. Hello, Ollie. So the only message to take from here, you're going to do a lot of, if you in your software ask for descriptive statistics, a couple of the things that you're going to see are the median and the mean. And by looking at those two, even before you look at a plot of the data, you can probably tell whether there's a lot of skew or large outliers to the data, and you can tell which direction it is just by looking at the difference between the median and the mean. All right? Yes?
And just to think of that, the mode will also be considered resistant to outliers.
Yes, that's right. So mode and median, those are resistant. Mean is not. Okay. So the percentile, which I've already been talking about, and which you probably know about already, is the percentage of the values that fall below a given value. So the 50th percentile is the value below which 50% of your data points fall. The 90th percentile, 90% of the data are below there. That's all it is. But it's a really useful description of your distribution, and you can describe any individual in a sample or in the population by its percentile for a given variable, and it's a useful way of putting data in context. And the quartiles are just special percentiles. They're the 25th, the 50th, and the 75th, and we use these a lot. They're what we show on box plots. They're just the median is kind of the center of the data, and the first and third quartile tell you sort of where the bulk, your most typical data lie. It's the middle half of your distribution. Now the range is a measure of the spread of the distribution, and it's just the difference between the extremes. It's the maximum value minus the minimum value. Anyone want to hazard a guess as to whether range is resistant? No, range is not resistant because it is in fact defined by your most extreme values. So range does not necessarily tell you anything about where the bulk of your data lie. It only tells you what your extreme values are. Okay, standard deviation. Now this is another very, very common, important standard measure of spread of the data. And it's more complicated than the range, but it's also often, it tells you more about where most of your data lie. And so we have another sigma notation formula here, which I won't. Again, if you really don't want to understand the formula, that's fine. I just want to give you the possibility of knowing what it is and being able to recognize it. So again, this is a sum. Here, the x bar is the average. It's the mean. So you would have to first go and calculate the mean value in your set of observations. And then for every individual, you would take its difference from that mean. All right. So for every individual, just you look at how different they are from the mean. You square that, you add up those squares, it's a sum of squares, and you divide by n minus 1. And you typically can get your software to do this for you. You don't have to do it by hand, but if you did, it wouldn't be so hard to do. That over n minus 1 is kind of an interesting thing. That's something to be aware of, whether you're calculating using n minus 1 or n. And n minus 1 is what you use for a sample and n for a population, which doesn't necessarily make it's not obvious that it should be that way. And I haven't even really talked much about samples and populations. But just know that if you have everyone in your population, that typically is calculated by dividing by n, and if it's just a sample, you would use n minus 1. So, and then variance is the square of the standard deviation. So you really do need to know what variance and standard deviation are, because they are used all the time to describe distributions. And I'm going to have a few more examples here to help with this, and we'll be talking about these lots more. So I just wanted to show you graphically what this calculation is. So if the formula doesn't exactly speak to you, maybe the graph does. Here I've taken a bunch of quantitative data points and plotted them along with a horizontal line for their mean. So this horizontal line is the mean, and the red lines here are the difference from the mean. So each of these red lines is the x minus x bar. And then I've done this for each of these different distributions. In this first one, the mean is almost right down near 0. You can't even see where it is. But the important thing is that we have the mean, that's a constant, that's the same for every individual, and we're just looking at how far each individual is from the mean. And then we're adding up. So this would be like adding up the length of all of these red lines, stacking them one on top of another to get the total width of the red line. That would be adding up x minus x bar. But as you remember, we will actually look at the squares. So this is the same plot, but I'm showing the squares, the squared deviations. So here you notice on the last page there were negative values, there were positive values. Here they're all positive because it's squared. And so the squared deviation from the mean is positive, and you can see it gets a lot more extreme. So this is part of why the standard deviation also is not resistant. It's not just how far each individual is from the mean, it's the square. So something that's really an outlier now, the square of that difference gets really, really large. So just some important properties to know about the standard deviation. It has the same units as the observed variable. So if we're talking about pounds, then the standard deviation's in pounds, etc. It measures the spread of the data, more or less. And I'm not going to get in today to just how it measures the spread. We'll cover that next time with the empirical rule. You might get to it in lab today, I'm not sure, but the important thing is that it is a good measure of how disperse your data are. And if it's 0 only when every observation is the same, so then there's no deviation from the mean. All right. Here I'm just plotting to show you again on these same plots where the standard deviation would be. So this for the normal distribution, and for the uniform distribution, the standard deviation, if you go from the mean plus or minus that, it's pretty close to where the boxes are, to that interquartile range. And when you go up to 2 standard deviations, it's kind of similar to where those whiskers are. And you know, values going outside more than 2 times the standard deviation it's probably an outlier. So you can kind of get the idea that you know, the bulk of the data is within 1 standard deviation, and then really most of it within 2 standard deviations. So you can kind of see how it's measuring the spread. There are, however, some alternative measures of spread, and we're not going to use these too much in this course, but you should be aware of them. The interquartile range, that's just the third quartile minus the first quartile. That's the width of the box in a box plot. This is a very nice measure of spread. That and this median absolute deviation. I won't talk about properties of those, just to have it down here in case you hear of it in the future. Those two are very resistant, and again, so adding some outliers will not change your IQR or your MAD at all, which is why it's good to know about them. And the range, which I mentioned, the maximum minus the minimum. All right, so we're going to wrap up now, and so you can get down to the lab and spend some time practicing all this stuff. So we covered the dot plot, histogram, the box plot, mean, median, mode. I won't go over all of this, but I think this covers everything that we're talking about in class today, and these are the things to take forward and try to remember at least what they are. So some of these things I do want you to be able to calculate, and you'll be practicing these again either in the lab or in the homeworks. That is actually, knowing what the mean, median, mode, range, and standard deviation, what they are, and being able to calculate them. You don't need to be able to write down the formula for standard deviation, but you should be able to calculate it. You should also be able to create histograms, box plots, bar plots, and frequency tables, and use those to identify skewed or symmetric distributions as well as outliers. I think that, yeah, that is our last slide. Do we have any questions from the class or from online? Yes?
Are the homeworks posted yet, like when they're due, or is that something that you couldn't find it on my website?
Yeah, I don't think they have been posted yet. That should be happening by tomorrow. Yeah, we will be posting a schedule of them, and it's just a bit of extra coordination here with the three of us. Yes, one more question, and I am noticing the questions coming online, and I'll get to those after this. Yes?
Would you be able to give us this questions?
Sorry?
Would you be able to give us practice questions? And is there any way we could submit the homework to you if you review it for us?
Okay, yeah, so practice questions, that's interesting. Yeah, I would be happy to come up with some practice questions, and I think that you will get some of those anyways in lab tonight, but if not, I'll be happy to provide some. As for going over your homework before you hand it in, I am also happy to do that. Just either come to my office hours or make an appointment with me, and we can review your homework. Okay, I'm going to take the questions from online here. When do you use dot versus histogram versus box? Okay, that question's from Paulette. Good question, and there isn't really an answer. I'm sorry, Paulette. Descriptive statistics is really more of an art than a science, and I would say a lot of times I will actually just try several things and see which looks the most interesting. After looking at everything and getting to understand the data set some myself, that's when I start making decisions about which to use, because I'm probably then going to be describing that data set to someone else, telling them something about it, and I want a figure to back that up, so I'll choose the one that helps back up what I'm saying. the best. That said, there are some guidelines in terms of what I put on that slide for the least detail to the most detail. If you want to show your data in as raw form as possible, that would be the dot plot. You're showing every single data point. If you want to show something more summarized, less detailed, then you would go to the histogram with different bin widths, and then to the box plot for more summarization. So it comes down to how precisely you want to show your data, how precisely you want to represent it. And there isn't a right answer. It just, I would say usually you want to show it in as simple a format that still gets your point across. Okay, we have more questions. Oh yes, can I repeat the questions after they're asked? I guess it's late now, but I hope, because those listening over the web cannot hear the audience. I hope you got, there was the question about, oh, wait, there's a follow-up question to this. Okay. Yes, and to answer, it's not that I'm not checking my Hunter account, it's that my Hunter account tends to have a delay. I don't get emails from it for 5 minutes or something till after it's sent, which is why I'm using my Gmail account. I think that is the end of the questions. So if there aren't any more questions from here or from the audience, we'll call that a lecture and meet again at, let's say, about 7:10 downstairs. And I'm not sure offhand myself how we're meeting up again, but I'll be there again to help you with that. We can go meet downstairs. I'll be down there with Ali, and if you're in Tony's section, you can come in and join Ali's or watch on a computer down there.